I'm here to say heretical things about the signatures that we might see around supermassive black holes and black hole phenomenology. So these are heretical things, but they might even be observable. So I'm hoping to be either proved decisively right or most likely wrong in the near future. So a basic roadmap of where we're going, we're going to be introducing effects due to positrons and axions using mainly GRMHD methods, or general relativistic magnetohydrodynamic methods, in astrophysical plasmas. The first application, I'm actually in charge of resubmitting to FiguresRevD after a referee report, so I'll let you know how that turns out. But this is GRMHD with the accretion of positronium plasma onto primordial black holes. Now, I said I was going to say things that are observable with EHT. We're not going to have resolution of black holes that are smaller than an atomic radius anytime soon. So this is building up to some of the methodologies and techniques that we're going to be using later, but it's an interesting application of how you can modify existing GRMHD frameworks into something completely different, but formally that happens to be fairly physically similar to other things we can do. So, I'm going to be starting chronologically, so the first 14 seconds of the universe is when this application is relevant. It's going to be in that era where you mainly had very, very hot and energetic radiation creating pairs, and those pairs of electrons and positrons are what we'd be accreting. So the accretion has one of the key things that GRMHD knows how to handle, which is the magnetorotational instability. And that will be our key into how this could possibly result in anything that we might see in the present universe, namely dark matter. The next application, so this is my day job, observing jet accretion flow black hole, or JAB simulations, because we want to get you to a dinner soon, so I'm not going to say the long name all the time. And what I've been doing with the Event Horizon Telescope often comprises of extending some of our emission models to add the effects of some less exotic particles, positrons, that we know exist because Sam was talking about them and other people have been talking about them. So not only do we know they exist, but they very well are relevant to the systems that we consider, like M87. So introducing those into these pipelines is, at first order, more correct than not having them in the pipelines, which is the default. So we're going to be observing the JAB simulations of M87. We're going to then put positrons in a semi-analytic model to see a path forward to how to incorporate them later on into GRMHD. We will show GRMHD models with positron effects in post-processing with an eye towards generalizing the simulations themselves to even have it in the dynamics of the fluids. Then we will go with GRMHD with axions in general relativistic ray tracing, which is more of a future direction than an established direction, but we get to talk about a lot of axion phenomenology in astrophysics and the prospects of using what we've learned in the previous parts to go forward. So, you can blame Roger for this slide, which is a very basic slide, but he told us to add the very basics that you've probably, at this point, all know from the previous talks. So I'll just go down with AGN, active galactic nucleus. It's in a mini region around the supermassive black hole that lights up as a discrete source. The accretion disk is the typically magnetized inflow that's gravitationally bound to a central massive object. They come in a number of varieties that some of us have pioneered here. I'm sure they're in the audience. Magnetically arrested disk and standard normal evolution are the two main plasma accretion modes that we're going to care about. The Stokes parameters are how we quantify the polarization in either the linear polarization directions with Q and U and the circular polarization direction in V. relativistic jets, some people here have also had something to do with those. We're particularly going to care about Blandford-Knatschek jets that's powered by the interplay of frame dragging near the horizon. Oh God, this is, yeah. And vertical magnetic flux accreting onto the black hole, as in this cartoon. Synchrotron radiation occurs due to, in this scenario, magnetic field lines that contain gyrating charged particle orbits around them. And then turbulence is something that can cause fluid motion to dissipate energy into particles. In particular, the magnetorotational instability is a good example of something that causes this. So, hidden figures, some of you might have seen the movie. Here's an extension of it. There are hidden figures in astronomy, and they might be under our noses in these simulations. So the typical astrophysical simulation that is used to represent a system like this, it is a system that has a pretty standard ionic plasma and it's behaving according to the rules of fluid dynamics in astrophysical plasmas, but they do a pretty good job of mocking up the real thing. So the real thing we actually observe, and we can tell if our theories are anywhere near the ballpark, and they clearly are near the ballpark. Then we've also have a whole population of black holes, as you can see here, that we've observed. So we have statistics now. We can do a number of different comparisons. So what more would we want to add? There's a number of observing prospects for the axion component. So there's the CERN Axion Solar Telescope, ADMX. So given these observations, what more would we want to add? Well, positrons are also often excluded in these ray tracing exercises that create those images that you see there, but they occur from a pretty well-established particle physics process, Bright-Wheeler creation of these electron-positron pairs. So this would happen with energetic photons in the vicinities of typical large AGN with energetic photons interacting with each other. So they should at least be modeled, and we have done this to see how these modify polarized images, and they have quite a strong effect. And what about axions and axion-like particles? So more with the background. So there is this parity, symmetric, odd parity, QCD Lagrangian that has a term theta QCD, that if you compare its value with the bare value theta tilde QCD, has to have some sort of really close value that might smack of fine tuning. So we know that this theta QCD, which governs things like the neutron electric dipole moment, has to be tiny. So how can you make something tiny, or in other words, how can you make the bare quantity theta tilde QCD very close to the renormalized quantity? Well, there could be some fine tuning going on with these matrices here, these quark mass matrices, or we could imagine a particle like an axion causing some chiral rotation of the system, and this axion particle would affect the dynamics. So this axion can have a number of couplings, and it also solves this strong CP problem, which the particle physicists are more interested about, but I'm interested in what we can do with the axions plugged into our systems. So they appear, axion-like particles also appear in beyond the standard model theories. So let's go into the status quo. So the specifics of the equations that we typically solve for GRMHD are conservation of mass in general relativistic form, and there are equations that govern the energetics via the stress energy momentum tensor. So if you have a stress energy momentum tensor, you can add terms that are the standard terms that relate to the pressures and energy densities for each species that we know, but there could also be terms due to viscosity and heating. So you can add physics just via that framework, and what you can get out of it, you can get out thermodynamics that governs the radiation by adding an entropy equation, Vlasov equation, and its moments. So these are fairly standard techniques that we could use in order to come up with an equation that gives us, in terms of whatever heating and viscosity, whatever physics you want to put in, the end result of this is a simulation that gives you a fluid with behaviors that have sensible patterns of densities being high outside of a centrifugal barrier for a jet, and or an outflow, and then you have higher densities in the disk. You have electron temperatures, on the other hand, having the opposite pattern, tending to be hot in this region near the simulation axis, and relativistically cold in the disk. So that's a typical setup, and it's typically done with just two species, electrons and ions, or in most cases, electrons and protons in the high energy situations we care about. So what happens if we use these well-known and well-established solutions to fluid equations, and we establish them, and we reapply them now to a context in the early universe? So again, we are resubmitting to FiguresFD as soon as I'm done with the talk, and this application, I'm doing it with my collaborators, my postdoc Brandon Curd here. And one of my PhD students, Nate Lujan at UTSA, and Thomas Kenneth Fowler. He was probably emeritus at this point at Berkeley, but I met him as a postdoc at UC Berkeley. I'm dating myself now, many years ago. So, so I started collaborating with him when he was only 88, and now we're still writing papers. So the setting that we start out with, again, we're going in chronological order with these applications. So from Weinberg's first 3 minutes, we're just going to take the first 14 seconds of the universe. At that time, the universe, being 10 to the 11 Kelvin, was hot enough where the prominent mode in which we would be creating particles would be through the energetic gamma into electron-positron pairs. So if you start just 100th of a second after the Big Bang, and then you take this into this leptonic epoch, you get about 1 billion pairs per proton. So if we were to use a simulation in this scenario, then the plasma would be electron-positron plasma. So in this radiation-dominated epoch, we can take us back to our Intro to Cosmology course. So the radiation-dominated equation of state, put it into the Friedmann equations for the evolution of the universe, using this relationship where the Hubble parameter goes like 8 out over A, of course, and it's 1 over 2T in the radiation-dominated epoch. So we can back out what the density of this universe is at various times in its evolution, depending on what the equation of state is. So here it's radiation-dominated, and we can use, let's use a CMB value for H naught if we actually want to pin down this number at a particular time. So we can pin this down at different times, including the time that we care about. So with these densities, let us see what happens under the analytic version of the work that we were talking about. So the primordial black holes can, they would accrete like any other black holes, provided you've appropriately seeded the universe with the density fluctuations that you need them. Once you have them, you can still use the scale invariance of a lot of the simulations in order to see what happens when you accrete the plasma onto it. And what we get is this this population of black holes between 10 to the 15th and 10 to the 17 grams. So the 10 to the 15 grams is important because below that, they would just Hawking radiate and disappear. So they wouldn't be useful to us for our application, where we want to evolve them to the point where they become black holes. But also, the fact that these still Hawking radiate but don't disappear, they can contribute to the gamma ray background. So there is a notion in which you can have too many or too little of these. So we can fix the overall normalization of this by the gamma ray background. So these things are not just completely, the imaginings of theorists and simulations. We have observations that these models have to conform to. So in the later version, where we actually care about the properties of the GRMHD, we realized it's critical that they're accreting under MRI rather than under Bondi. And the particular plasma, again, it's the electron-positron plasma component of this, and particle theorists have computed in this leptonic error how much of the density rho would be in the photons, how much of it would be in neutrinos, how much of it would be in electrons and positrons. And we would take about a third of that density, and that would be the positronium component of it. And when we actually consider the different accretion modes, if we use Bondi accretion and we pretend the plasma isn't really rotating, it's radially accreting, and V is approximately C near the horizon, using the ambient density that we calculated from the universe's conditions, the black holes would grow to be enormous. So they would break every astrophysical model that we would have if it were just Bondi. So that can't be what's going on. So again, probably boring you with the slide because we've already seen the magnetorotational instability in earlier talks. But if you imagine a disk as being composed of differentially rotating rings, then these rings can exert forces on each other that tend to slow down particles that happen to lose angular momentum and fall in, but that also tends to increase their angular velocity, and you have this runaway effect. So as Roger likes to say, the MRI is a victim of its own success. It can create these MRI turbulent features, as you see from these vertical slices, where the black hole spin axis is going up in this paper that's I had with Ken Fowler, Huili, and myself, obviously. And you can have the MRI create turbulence in a disk. So this MRI also is useful to us because it changes the way that the accretion goes. And now dmdt of the accretion looks like the Keplerian speed. And under this MRI, again, accreting with the ambient density that we had, we have radius mass relationship, and we have MRI scales that are in this calculation that give us an accretion rate that's, dmdt is roughly some number C times M over T, where C is suborder unity. And we end up getting a accretion scenario where in the simulations, we've seen that the radial velocity is starting to approach the Keplerian velocity, or proportional to it. So the Keplerian velocity is in these dot dashed lines over here, versus V goes like velocity goes like 1 over the radius squared is on this faster path. So most of our simulations at the different times do have the radial infall the way that we predicted, reminiscent of MRI. But also there are these MRI wiggles reminiscent of the type of instabilities that the MRI can produce. And we see that also in the m dot as a function of radius, and in the magnetic field normalized as a function of radius. So we see the evidence of the MRI in the simulations as well. So if we go close to the black hole, what the accretion looks like is that far away you have the roughly vertical field, but then the field ends up changing its geometry as you come to the black hole. And doing our integrations of how much accretion you're going to get, it ends up being a population of primordial black holes that doesn't get too big to break our observations in that the black holes would be observable in every single corner of the universe. Doesn't break our observations in that the black holes are so small that they would have radiated away, and the black holes are just big enough to produce some amount of Hawking radiation that we integrate up that is consistent with the gamma ray background. So, I'm not betting a house on it, but it isn't broken completely at this moment. So that's just the upshot of what we've done. Yeah, go ahead.
Hi, Columbia. Presumably in early universe, there's no magnetic field.
Well, depends on how early you're talking about. So we're talking about a second after the Big Bang. There might have been some, seed field, some.
Yeah, the question is, what are you in your simulations? What are you actually bringing in? What field? What field?
Yeah, it turns out that almost any fields that we have would be amplified. There are dynamo processes that, as long as you have any seed field, it doesn't matter. It matters that when you did have, what created the earliest magnetic fields in the universe, that's something that we really have to make assumptions about. We have almost no way of reliably saying it, so we just have to assume that some field that's there could potentially be increased or decreased, and because of the dynamo effects in these plasmas, these fields are going to grow up. So yeah, like you could probably ask someone across the street what the actual fields at the very beginning of the universe were at the CCA or at the Center for Computational Quantum, but that's something that is a little bit beyond the scope of what we're doing here. Go ahead.
Mitch Spiegelman, University of Colorado.
Mm-hmm.
The magnetic field issue might be significant because I think your field has to be large enough so that your gyro radius is not too much bigger than the Bondi radius. Otherwise, you're not going to get dynamo effects. You've got to magnetize the plasma.
Yeah, so we started with a few different simulations with different magnetic fields, and we haven't done much fine tuning, but in order to check whether it's a natural amount of field, it's
MHD already assumes that.
Oh, it's already
zero, right?
But, okay,
That MHD won't be able to tell.
yeah. So there's just a precondition that you don't know about, but you're just assuming it's how.
yeah. In order for it to go forward, we have to be able to put something in our simulations. But thank you. So.
Is there a question?
Yep.
Yeah.
Sorry, they refer to your question?
Yeah. From the density of the ambient gas, could you estimate the optical depth of the accretion there?
Well, sorry, these are primordial black holes. So you asked from the density of the ambient gas, could you estimate the optical depth of the accretion disk? Yeah, I don't even know if it's appropriate to call it a disk. And the radiation that you're thinking of, what radiation are you thinking of traversing this so that we have an optical depth? Like what type of radiation are you talking about?
Hawking radiation.
But the optical depth of Hawking radiation?
The universe is completely opaque at this stage for anything.
Yeah. Yeah. I mean, there's a bath of very, very, 10 to the 11 Kelvin photons, and yeah, it's extremely opaque.
Yuri,
Even less, yeah.
Yuri.
So Richard, can I just ask, MRI so you have some rotation, but where is the angular momentum coming from? I mean, this is the perturbations largely linear, like cosmic people.
Well, the question is deeper. Why there is no Bondi accretion? Because you need this very significant rotation to avoid Bondi.
But, yeah, rotation. How do you treat this rotational force?
Well, whatever seeded these black holes might have just come with the angular momentum. So I don't know if the assumption that these black holes just come from these density perturbations, but nothing in whatever seeded these black holes had smaller seeds earlier. They had accretion from the seed size to become larger. So the accretion itself might have added angular momentum, but they also might have been created with angular momentum. So there are two ways they could have gotten the angular momentum, and they do accrete, so the accretion itself might do it as well.
It's just that there are some computations in literature actually about the initial spins of those primordial black holes. The conventional computations, the conventional scenarios give low spins.
But even if they start out low, they do accrete. So yeah, that could add to it.
Let's continue and.
But thank you. These are good questions. Thank you. So conclusions, tentative conclusions, of course. But we've made a model that doesn't immediately fall flat on its face. That has primordial black holes that are able to be analyzed by general relativistic magnetohydrodynamic simulations in an environment where the plasma density is a positronium or electron-positron plasma, and we have the same type of tools, namely KORAL simulations, that do radiative general relativistic magnetohydrodynamics that show these plasmas developing magnetorotational instability and accreting onto these black holes in a way that lets them grow to the point where they can leave a stable dark matter relic, and they could also contribute to the gamma background. So we have, in this realization, tens of % of the dark matter is coming from this contribution. Our sweet spot is roughly 30% in what we're going to send out. And the gamma ray background is still not breaking the observations. So our next application. So yeah, again, my day job. I use general relativistic magnetohydrodynamic simulations with many collaborators in order to infer what processes energize the particles that are contributing to 230 gigahertz emission around the sources that Event Horizon Telescope can see. So we can add positrons in here, and we can actually get things that we could directly observe through very long baseline interferometry. So we start with some basics again. I know we have a very broad audience here. So radiative transfer links astrophysical source properties like emissivities to observed properties by doing either this line of sight integral or a more general one where you have astrophysical effects, including those from absorptions on each polarization direction in the Stokes parameters that we mentioned above, and Faraday components for rotation and conversion, so rotativities and generalized emissivities for the polarization. And the way that we can model the different physical effects in this is through the radiative transfer coefficients themselves that we're getting our polarized intensities, so I, Q, U, and V. They depend on properties of the plasma, like the magnetic field. They depend on the observed frequency. And they also depend on the assumptions that we make for what the population of the emitters are. So this PE is a pressure for relativistic emitters, but we didn't say whether they had to be positrons or electrons. These PEs, we can make assumptions for how the number density of these changes with the energy of the or the Lorentz factor of the electron or positron. So, we can put in a thermal variety of these coefficients where you have the number density go in an exponential way depending on some temperature parameter. But you can also have a parallel assumption. You can think of astrophysical shocks as affecting these in some situations. And you can put these recipes or these physics into your radiative transfer formalism, and then you could see how this changes what you're observing. So the tools that do this, some of us have our pet tools in this room, but IPOL, GR-Trans, KORAL, RADPOL, there's too many that could fit in this slide for the allotted time. So one classic example of, here's how we've done this in the status quo. Here's a common application of this. So the EHT simulation library for M87 has tens of thousands of ray traced images from different models. These models have a heating prescription that's governed by this Greg House-based turbulent heating model that was actually based on the solar corona. So we have we have a behavior that's the ion to electron temperature ratio of a plasma is governed by the gas to magnetic pressure ratio of the plasma beta, where that at low betas or at low betas where the gas pressure is dominating in the relativistically cold disk, we have the ion temperature dominating, and this function behaves like an arctangent function, asymptoting from R low to R high, and then in the jet region, you get that sort of variation to having R high govern the electron temperature at high betas. But that's not the only way that you can transition from those regions and still replicate the behavior of plasma, say in the solar corona. or in the vicinity of a black hole or its magnetosphere. There are other parameterizations we can use, but using this parameterization and using a simulation library that has different spins and different SANE versus MAD magnetizations of the plasma, the basic idea is that you could have the different parameters effects being teased out in the simulation library. So it turns out that the zero spin models in this in the second and the fifth column are the ones that are the most symmetric, and those actually end up being ruled out. So those models ended up being observationally too symmetric and didn't have enough jet power. So the Blandford-Notchek mechanism is possibly at work here, creating the jet power in the M87 jet and making a inner horizon, horizon vicinity magnetosphere that looks like the observations. So in the extreme spin cases, the MAD simulations on the left half have more spiral electric vector polarization angles. So with the orientations that we have in the sky that we believe M87 is, we believe that those spiral EVPAs correspond to vertical magnetic fields creating onto the black hole. So another necessary component of the Blandford-Notchek mechanism. So according to the simulations, this vertical magnetic flux on a spinning black hole is a good step forward to interpreting what's going on with this emission model. And there's a relative insensitivity to the R parameter. So R high doesn't make too much of a difference in what you see here, but it does change the locus of where the emission is brightest, whether it's near the inflow or whether it's near the funnel. So with this, we can generalize this. So one of the ways you can generalize the emission prescription is to change how you assign electron temperatures to what betas the plasmas have. So you can have a prescription where instead of having a variation look like an arctangent with two asymptotes, you could have this electron to total temperature ratio be an exponentially falling parameter in beta, and it could be governed by this exponential constant beta crit that determines how steeply or how cuspy this transition is. And this has some advantages that you'll see in maybe Haley West's poster out there. You can have another model where you have constant beta E, or the constant contribution to the electron pressure from constant electron pressure to magnetic pressure ratio inside a jet region. And this is a model where you basically have the magnetic pressure sourcing the energy in particles. You can think of something like reconnection affecting something like this. You can think of this as being subequal partition, but equal partition for our parameter beta E not equals 1. So we put this model in our jets sometimes. And we can generalize this to have a model where you have this electron pressure scaling as powers of the magnetic pressure to get the collimation profile if you have a roughly B power law in cylindrical radius variation. So you can get a nice control over the collimation if you use this model. So we can also incorporate past the status quo the positron effects. So positron effects, we've talked about where they might originate. So they're energetic processes like bright-Wheeler pair creation that occur in Compton clouds that may scatter the soft photons around the funnel. So you have photon-photon interactions that could leak into the into the jet to create the pairs. So these calculations give you very low densities of positrons for a source like Sagittarius A star, but positron content that's above Goldwright-Julian for the M87 in terms of the density, how much density of pairs you're creating. So these can be important in M87. And you have spark gap processes, which are getting bigger for bigger AGN. So we've talked about some of these potential gaps that occur where plasma has to inflow near the black hole, but then centrifugal forces force them out away, and you have a charged region. And in that charged region, you can get these pair cascades. So there are reasons why there should be pairs, especially for things like M87. And if we want to now put these into the GRMHD plus G general relativistic ray tracing setup, how we do that is we modify the ray tracing components, assuming charge neutrality. So here are the modifications for implementing a positron ratio into a ray tracing setup, so you can modify your radiative transfer coefficients. And the positrons don't affect the dynamics of most of these plasmas too much, so you can consider them as a radiative effect. And you could then put these modified radiative transfer coefficients into formalisms for what the, let's say, emissivity function is. So fundamentally, the emissivity function, if you have a direction, a normal direction to the observer, so the observer plane is determining polarization directions, you can take each polarized component of the emissivity and relate that to the partial pressure of the electrons or positrons contributing to the observed frequency. And then you can put that into a framework where you can prescribe what this PE is, either in phenomenological models like the constant beta E model, or you can just modify the radiative transfer coefficients, and you can include positrons into your ray tracing setup that now you have a way to control how many positrons you're creating. So if we were to do this with a general relativistic ray tracer like GR trans, we can see that having no positrons on a image of a near horizon model of emission in the constant beta E model for this jet doesn't look too different than having positrons in there, where you have roughly a mix of half of your plasma is pair versus half of it being ionic. But the total intensity doesn't tell the story. The polarized intensity actually gives you a much greater linear polarization fraction. So you see these axes for Q and U go up to values like 80 here, but then they go up to values like 40 and 60 here. So there's a lot more linear polarization you can get if you increase the positron fraction. And the positrons, because you have coupled radiative transfer equations, if the linear polarizations are going to change, you're also going to change how the circular polarization pattern looks. So this also depends on the constant beta E parameter, beta E naught. So if we tune that up, then the whole setup also becomes even more mixed. So you can think of this as some sort of tuning parameter in that matrix, and you can add even more mixing there. So even at total intensity, go ahead, yep.
Sorry,
Yeah, go ahead.
yeah, my question is, you cited a number.
Can you use the...
Oh,
Yeah.
I am. Okay.
Yeah.
You cited a number for the estimated positron density for the M87. I just forgot. How does it compare? Well, in other words, what's the F-pos in reality if you take the density of electrons and take that estimate for the positron number?
So the F-pos from that calculation that was or a couple of orders of magnitude above Goldbach-Julian applied to the funnel regions. So it wouldn't be exactly what we're doing to paint the entire jet here. So at this stage, the next step in this project would be to locally vary the positron fraction, which we need to do. But it's not an apples-to-apples comparison because we are painting the whole region of the jet with this positron fraction that's is like completely mixed plasma. So you can think of this as also having contributions from the gap. So it's not an apples-to-apples comparison to just say that number above is what we put in here, because we're considering what's just a reasonable number of positrons for a jet who's evacuated because there's a centrifugal barrier, so there may be very little plasma in there.
This is not This is not the matter in the jet emitting, right?
We paint the this is a jet emission model.
But then the density doesn't make sense, right?
The density is the density we get from a semi-analytic model that was fit to a simulation. So there's a little bit of, so this is not a completely force-free jet. As we know, there's almost force-free. And there's a little bit of density in there. And then we can say that whether that density is the original electron-proton plasma or if it's more electron-positron plasma, we can parameterize that.
Well, the reason I'm asking is basically as you move to more force-free region, yes, I mean, you're dominated probably by electron-positron plasma, but as you move to regions where you can actually trust, this F-pos probably becomes like 0.
Yeah, I understand the point about density floors adding a comparable amount of plasma to that would be in the
That's a different,
in the simulation, but the mass loading makes this model a lot less relevant for the way that we're causing the emission. So, but there's enough uncertainty that we can probe it with just the parameter survey. So if you look at this paper, we have a pretty extensive parameter survey. So you can imagine whatever is your favorite possibility. All right, so, but if you just do this exercise and you see what the first order effects of having positrons into a jet model for emission are, you can look at the total intensity again. It doesn't tell you the whole story. So if we just change the power law index, if we assume a power law is what's the energetics that's driving the population of emitting particles, then the power law at the optically thin part of the spectrum just obeys what the power law case total intensity just obeys what the power law index tells it to do. So you can put the observations here for total intensity spectra, and the curve is just going to bend regardless of the positron fraction in terms of what the power law index is. But when you look at the polarization, that's when the F-positron has a comparable effect as the power law index. So at the low frequencies, even below 230 gigahertz, you can see there's a very pronounced effect of the F-pos, which is the difference between dashed, dot dashed, and dotted lines, versus the colors, which is the power law index. So the positrons have a comparable effect at the low frequencies as the power law index would. And if you look at the circular polarized component, where we don't have as much data, the circular polarization has a really neat signal for what happens when you increase the positron fraction a great deal. So you can't make enough Faraday conversion to support in a symmetric electron-positron plasma enough V to have the V persist high frequency. So all the dashed lines, which means all the highest positron content plasmas, have a very sharp decline in the Stokes V at the high frequency spectra. So this is not exhibited in any of the other positron content. So this could be a probe if we get data out there for which models have the different positron content. So there's a RIAF model that we can also make using this formalism. And I'm just going to go through this fairly quickly because I do want to leave some time for the last applications of the axions. So the RIAF model was this Broderick and Loeb RIAF where the temperature was given geometrically. And we just chose one of the Broderick and Loeb parameterizations to see that for a Sagittarius A-star model, you can apply this. And you can see what the effects on the polarized images would be for Sagittarius A-star. But this is more of a theoretical exercise because we don't expect there to be much of a positron effect in a source with as low of a compactness quantity as Sagittarius A-star. So we can do the RIAF spectra, and they have the same patterns as well. So they have the same patterns where at the low frequencies, the positron fraction has a strong effect on how much linear polarization the spectrum is going to show. So we also have movies. You can again look at Haley's poster that shows when you finally put these positrons into general relativistic ray tracing on top of gyrometry simulations, you have the MAD simulations or magnetically rested disk simulations have the V over I decrease linearly with the addition of positrons because the positrons are canceling out the circular polarization of the electrons almost linearly in like the proportion to how much you add them. But for the SANE simulations, there's no such pattern. It's not monotonic how V over I changes when you increase positron fraction. But the EVPAs rotate very, very wildly with just a small change of positron fraction. And this is because the Faraday effects are about 1,000 times bigger in the SANE than the MAD for them to have the same overall intensity. So because the magnetic fields do all the work in creating the intensity, in the MAD case, you don't need as much density, but in the SANEs you do. And in the SANEs, that density gives you a lot of Faraday thickness, and it creates this EVPA rotation that's a key signal for whether you have a SANE plasma plus changing positron fraction. So we can see the SANE and MAD over time. The MAD actually had that behavior where the V over I increases linearly in the positron fraction, only for time steps when there was this flux eruption event. But there wasn't this behavior in all the time steps. So there's also some interesting reanalyzation we can do for the pass-fail tables. If you use these models and you include the positrons and you compare SANE and MAD and you also include critical beta models, it turns out that SANE simulations actually had a lot of resolved local values of linear polarization M conform with the data. So the median model, if it conforms with the data out of all the time sets we use, then we put it in bold. So it turns out that for this resolved polarization, the SANEs actually did pretty well. But for the MNet, where the MADs had more symmetry and you average out the polarization, the MADs did better, as one might expect from the beginning. So expanding our phenomenology does help us determine things about these systems. And of course, again, I mentioned that not all the times that V over I decreased linearly as you added positrons. This is shown here. So this is one time step with different emission models showing the V over I having this roughly linear monotonic variation with positron fraction. But the other time step in the dot dash curves doesn't exhibit that behavior. And there are flux eruption events that also tend to coincide with this pattern of behavior, the decrease in V over I as you add positrons. And so it happens at times that tends to be when these flux eruption events, where phi dot spikes and m dot has a trough occur. So, I'm going to save these for my final conclusions because I do want to get into the axion applications above. So, So in the last 10 minutes, we started with the first 14 minutes of the universe. Now we end with the last 10 minutes of the universe. Just see if you're awake. So we have GRMHD axions with axions in the general relativistic ray tracing. So we're building this up. So this actually stems with when I was at the CCA for 3 months when Harvard was locked down for a pandemic during my postdoc. I came down here, started working with Stefan Alexander, Ken Van Tilburg, David Spergel, really nice little foray into this new physics for me. So the types of approaches we can use to find axions, I lump into 2 categories. There are approaches that show that, that have the axions. The axions can couple with the standard model in many different ways. So we have a general field theory approach where we just write down all the interactions that we can imagine, and then we see where there's an astrophysical context where this interaction will show up. So we write down the Lagrangian and Feynman diagrams and assess the detection prospects. So we want to avoid reinventing the wheel because there are all these papers out there. So why don't we just try to write down the most general type of Lagrangian with all these interactions that we can think of, and then see what happens in each of these scenarios. But there's the observationally driven approach. So we could, we know that we have instruments all over astronomy that can view jet accretion black hole systems or JAB systems all the way down to the horizon. We know that where the SEEKS collaboration, so the compact sources are both black holes and neutron stars. So we also consider gamma ray bursts. And we also know that interesting thing happened in the early universe. So why not just see if we can get any of this phenomenology in these scenarios? So there are observations, of course, that tell you that the axion mass is not unconstrained. So you can only choose certain axion masses if you want to have them have any appreciable coupling, just based on all these wonderful experiments I'm sure some of you are part of. So let's put this first approach into action. So let's use this Lagrangian approach. So the electron spin magnetic moment has potential corrections that you can write down to this term G minus 2. So you can correct this using some sort of axion term A in some sort of interaction Lagrangian. And you can have this process of axion pair production contribute corrections to that interaction. So this axion pair production has some, of course, kinematic limitations. And you can also imagine different processes that involve axions, such as axions coupling to a two-photon vertex, so a Primakov interaction where the axion axion field strength is here, and you can make a dimensionless coupling out of this C A gamma and FA. So you have terms that relate to the axion coupling, the axion field strength, and you have an interaction like this. So this is part of our field theory approach, and we have we can make some sort of perturbed linearized quantum field theory, including all the interactions that we can possibly think of, more interactions. Let's think about scattering. So we've shown Bright-Wheeler, but what about when Bright-Wheeler involves an axion term? So we might be able to even come up with an astrophysical scenario where this is relevant. So inverse Bright-Wheeler. So we really don't want to reinvent the wheel. So let's consider broadly what type of interactions we can have. Compton scattering with axions. So we can write down a lot of diagrams, a lot of interactions, but can axions be a significant source of radiating pairs? So let's think maybe this axion pair production might outcompete in the context of gamma ray burst pair production that's governed by some optical depth for our conventional gamma-gamma interactions to pair production. So what if you have a high Lorentz factor that can make this optical depth much smaller? So what if we make this a lot more optically thick? So what if we really try to suppress the astrophysical contribution to the pairs? Could we get an axion contribution that picks it up? So maybe if we try to use some reasonable values for the luminosity, for the energy, and for the time scales, maybe we can have some sort of axion pair production that can compete with Bright-Wheeler. So this is a very preliminary scale, but we have a condition that this optical depth would have to be bigger than 1 over G A gamma gamma squared in order for these processes to be comparable. So again, this is just brainstorming at this stage, but there is a reasonable prospect for having astrophysical contributions to pairs that could radiate being very small, and couplings that we can look for that can make the axion contributions big. So that's one idea. So let's just go with some more of what type of settings we can find these axion phenomenologies in. So what about Compton scattering? So you saw this Compton scattering diagrams and you saw the interaction. So could there be some sort of interaction with the scattering that we can calculate the energy rate and the energy loss from? So that's one avenue we can go by. So if we can see in a radiatively inefficient hot accretion flow, using this type of interaction, how much energy we'd be losing to axions, maybe we have a very, very optically thick disk, and we have a lot of this interaction going on with the axions. We can potentially find the source of missing energy from the axion contributions that might be comparable to the luminosities of very low luminosity AGN. So again, these are sketches of ideas. So other ideas could be, we can have some sort of non-perturbative axion term with A of t in a time-dependent sense, and some sort of amplitude that we can compare to the size and rotational frequency of a neutron star. So could we have neutron star resonances with these axions? And as a neutron star rotates, what if these resonant processes that couple the rotation of the axion with the rotation of the neutron star with the axion magnetically break the neutron star, and then there's going to be a key. If we have any way to magnetically break the neutron star, and then it ends up having some sort of resonant frequency with the axions around it, then we could have a cascade of axion that again gives you missing energy through this process. So if you want to calculate the actual superradiant properties of neutron star bound states, there's a reference from Day and McDonald. So this is one mechanism where you could see in a missing energy in a pulsar that there may have been an axion cascade based on this type of resonance. So this is the main avenue that I wanted to show in the last 2 minutes that I'm going to talk. So axion superradiance around supermassive black holes is an idea that Yifan Chen has done a lot of work on. And if the axion mass is such that the Compton wavelength of the axion is comparable to the size of a black hole like M87, which is determined by its mass, you could have this superradiance where you have an axion cloud developing due to the boundary conditions that this satisfies, and then this actually couples to the E&M radiation. So the axion cloud that you make there has some GA gamma coupling that you can use to rotate the EVPAs. And this rotation of EVPAs actually has a very characteristic form. It looks like it's the hydrogen atom intensity in terms of the axion amplitude. There's a rotation of the EVPAs that are due to the photons leaving the system. And this would only occur if there are this type of phenomenology. So if you compare it to other phenomenologies where you have, for instance, positrons causing EVPAs to rotate, it looks completely different. So I'll leave it there. Thank you for your questions, and I look forward to more.